All right. Hey, everyone, and welcome to the post-exam 3 review, or the review toward the final exam. Or we'll be reviewing, or my plan is to cover all of the sections that happened after exam 3, but that you'll definitely want to know for the final exam. Uh, for posterity's sake, this is the spring semester of 2024 for Math 234, multivariable calculus, and last but not least, I am your host, Steve Dragoo. That's me. I'm that guy. So if you're looking through the notes to try to find a written record of this review, you can look over to the left to see the directory information for where within my notes this review is contained. So it's just in my notes, the exam reviews tab, and then, post-exam 3 review. That's this one. There's also the other reviews for exam 1, 2, and 3, which are probably worth looking over before the exam. But in an effort to not make I don't know, like a 6-hour video, some Tim Rogers length video, I'm just going to focus on the stuff that's happened since we took exam 3. And hopefully I can get that done in like an hour and a half or something. I don't know why I cursed myself by putting a time on it, because now I'm guaranteed to go over that number. But, well, it's not like I'm going to edit this video. All right, enough pomp and circumstance. Let's get going. So, very first thing I want to talk about is a bit of a general overview of the major 3 sections that happened in this post-exam 3 review. So those are all Green's theorem, Stokes' theorem, and the divergence theorem. And, as you've probably noticed, all 3 of those sections are pretty hard. That's a very common sentiment. I think just about everyone who goes to learn multivariable calculus, nobody really fully understands these sections their first time through, or at least I didn't. And look at me now, I'm teaching the thing. That's about when I finally figured out how these things work. So I want to try to at least do better than me of the past, and see if I can get a better understanding of how these things work. So a big thing that we looked at for trying to make sure that these like Green's theorem and then ultimately into Stokes' theorem stuff work is by looking at conservative vector fields. So I've got this first example all written out, and you might even recognize this from the exam 3 review because I talked about it there too, but I thought it was important enough to bring it up again one more time. So when we say we've got a conservative vector field, that just means that the field that we have is the gradient of some scalar function, right? So this field gets to be the derivative of something else. And it's all 3 parts of the field all line up to have come from the same single scalar function, which is a bit of an interesting idea. That. So we've got, say I've got the field that's right here, the one that's laid out in front of us. I want to, again, assume that if I'm trying to check to see if it's conservative, I'm assuming that that field is the gradient of a function, which means that each of the 3 components, which we usually label P, Q, and R, just because we can go in alphabetical order, are the partial derivatives with respect to that component. So we want to assume that P, the first component of the field, is the X partial derivative of some original scalar function. And then ultimately, if we're going to say that a field is conservative, that means we're interested usually in finding that original function. And then, yeah, to follow that all up, the Q component is the Y partial derivative and the R component is the Z partial derivative. So if we want to check to see if that's true, to see if this thing is a conservative vector field, if that function should exist, then we want to check all of the mixed second order partial derivatives and see if they're equal. So effectively what that means is, like, if I take an X partial and then a Y partial, I should get the exact same thing if I take a Y partial and then an X partial, because for the most part, as long as we have a nice enough function, and we're only really looking at nice enough functions right now, it shouldn't matter which order we take a derivative in. we'll get the same result as long as we do the same two variables. So we're going to assume that we already have partial derivatives when we've got P, Q, and R, and we're going to complete the missing partial derivative and check to see if it worked out, which is what this table is doing here. I'm assuming P, the first column, is already an X partial, so I want to look at its Y and Z partials, and then compare that, since I'm assuming P is already an X partial, if I do the Y partial, I want to compare it to the other XY partial derivative, which means Q partial X. And I see I get the same thing when I do that. Looking along that first row, I can see that both of my XY partials come out to 2YZ cubed plus 1. Looking across the second row, I can see that my XZ partials both come out to 3y squared Z squared. And across the third row, I can see that both of my YZ partials come out to 6xy Z squared. So for some reason, I decided to switch to Z halfway through. Someone watching the video will think that's either very funny or incredibly annoying. So, hey. Next up, we know that our field is conservative, so we could find that original scalar function, which means I want to integrate each of those components back up to find the original function, and I'll integrate each component with respect to the place that it is. So I want to integrate P with respect to X, Q with respect to Y, R with respect to Z, and I should see the same terms showing up each time I do that, or at least some similar terms showing up each time I do that. It's like when I integrate all three terms, I see this X, Y squared, Z cubed term that shows up in every single one of them, because that term, when I take its X partial or its Y partial or its Z partial, that term should show up in each partial derivative. Whereas something like XY, so I'm adding that plus XY right here to the end of my X component term. If I think about taking its partial derivative, I'm only going to see that show up. If I'm thinking about taking the partial derivatives of XY, I'm only going to see it show up in the X and Y partials, but then not in the Z partial, because there's no dependency on Z, so its derivative would be 0 if I did a Z derivative. Because then after I integrate back to all three of these guys, I expect what's up there? I expect to be able to piece all of these back together to find the original function, which is the part I've got right here. Combining up all of my unique terms, I've got an X, an XY, a Y, and a Z. All of those came from the individual integrals. But that X, Y squared, Z cubed showed up in all three, and I only want to add it in. I only want to add it in once. I don't want to add it every time I see it. I just want every unique term. So that's my original scalar function, f, that makes this thing conservative. And then, yeah, I wrote down that other note here. It's not the sum of all components, but is instead the union of all the unique terms. And the final check we do is like take the gradient to see that we do come back to our field F. And the next slide in my TED Talk is this diagram right here. Grabbed it from the textbook. I know I put it in my divergence theorem notes, but I think that this diagram kind of illustrates the various uses for the three new theorems that we've learned and what it is that they're really doing. Because each of these new theorems, Green's theorem, Stokes' theorem, and the divergence theorem, are all effectively some extension of the fundamental theorem of calculus into multiple variables. And if you can learn one sort of core thing, one sort of core idea about these three really hard theorems at the end of Calc 3, it would be this right here. Green's theorem, Stokes' theorem, and the divergence theorem are all an extension of the fundamental theorem of calculus. That fundamental theorem, in case you've forgotten, is the one that tells us if we integrate something between A and B, then it's equal to f of B minus f of A. That's our fundamental theorem of calculus. It's the one that's up there at the top. And what these fundamental theorems all are saying about the thing that we are integrating is that if I want to take some object that I'm going to integrate over, whether it be a line, a curve, a region, a surface, or a solid, those being the 5 options that are in the diagram, if I want to integrate over those pieces, those objects, whatever they are, I can solve that definite integral by instead evaluating an antiderivative at the boundary of the object. So when we're all the way back in Calc 1, our very first fundamental theorem, we said that integrating from a to b over an interval a to b, I could instead just evaluate the function at its endpoints, a and b, or its boundary points, a and b, to figure out what the integral looked like. Then when we extend that to the fundamental theorem for line integrals, we'll add a few extra clauses in there to make sure that the function that we have is nice. But we'll say that even if it's a curved line, we can still evaluate a line integral by evaluating a function at the boundary points, this being, again, a and b. When we extend that from a one-dimensional line into a two-dimensional area, or we usually call it a region, D, then we're integrating, some area, and Green's theorem says that we can take this double integral over an area and turn that into a single integral along the boundary curve. And a thing that we're going to notice about all of these fundamental theorems is that we always reduce the integral count by 1 when we move to the boundary. So it's about taking, instead of having to evaluate over an area, we can instead evaluate along a curve. Stokes' theorem says almost the exact same thing as Green's theorem, integrating over a surface this time instead of a region, but we're still going to say that this double integral over the surface is equal to a line integral along the boundary of that surface. And I say that Green's theorem and Stokes' theorem are almost saying the same thing, because Green's theorem is like a very specific case of Stokes' theorem. Both of them look at some thin, I'm going to call it a thin 2D object, whether it be a thin curved surface out in space or a flat area in the plane, for Stokes and Green's respectively. So the real difference between the two theorems is that in Green's theorem, we are working in 2 space, right? We only have our 2 variables, x and y. So Green's theorem is in 2 space. We're in the coordinate plane only, and we have a flat area, whereas Stokes' theorem is going to basically say the same thing, except it's a thin, potentially curved surface that exists in 3 space instead of in 2 space. So that's the real major difference between Green's theorem and Stokes' theorem. Green's theorem is just x and y. Stokes' theorem is x, y, and z. But both are looking at thin areas, whether it be a flat region or a curved surface. Then the divergence theorem is going to step that up one more time. Divergence theorem is going to say that the triple integral through a solid region, so now this is a 3D object that has density or mass, or it's a filled-in solid instead of just a thin shell. So a triple integral through some solid is equal to a double integral over the surface of that solid. In fact, that double integral is a surface integral, which was the other super fun section that we had right here at the end. So this diagram right here is maybe my favorite, well, probably my second favorite picture I have included in my notes. And since I liked it so much, I decided to spend a few extra minutes talking about it. Hopefully you liked it too. But all right, let's take this thing to our first actual problem. We're only like just over 10 minutes into the review. Time to finally actually do some math. So let's see what we've got here. We want to calculate the integral of f dot dr, where it's some curve of a region D has an area of 6. And we're going to use Green's theorem to do it. So on the subject of using these theorems, a tip I can give to help you kind of get through some of these problems. In particular, when we say use Green's theorem to evaluate blank, or use the divergence theorem to evaluate this other double or triple integral. Anytime we say use that to solve this, it's like in this particular case, use Green's theorem to solve this line integral, the actual work that you should do is the other side of the theorem that isn't given, right? So if I see this question that says use Green's theorem to evaluate the line integral f dot dr, the actual work I'm going to do is the other side of Green's theorem, the one that's a double integral over a region. And that's basically always the case if it's a test question. If we say, use the theorem to solve this thing, we're really saying switch it over to the other side of the equation and solve that instead, because it's probably a lot easier. So in particular, this problem right here with the information provided basically can't really be solved unless we switch over to the other version of Green's theorem, the other side of the equation. So let me start writing some stuff in. We want the line integral of f dot dr, where f and dr are vector values. So we'll put hats on them. And I'll write out the second half of Green's theorem here in a second. Quick note on some of the notation that'll show up. This tends to be more popular in disciplines like physics or engineering, but sometimes an integral sign has that little circle through it, the one that I just drew in here on the left. So some integrals get a little circle in there, particularly when we're doing line or surface integrals. And that circle through the middle of the integral simply means that whatever I'm integrating over is closed. So I have a closed boundary curve. I have some closed loop that I'm integrating through. That's what that circle means. Closed loop. So we just draw a little circle in there. Don't let that notation fool you if you see it anywhere. It still just means we're integrating. We just got an extra little symbol to talk about the thing we're integrating over. All right, I want to say this thing's equal to the other side of Green's theorem, which says the double integral of q partial x minus p partial y dA. Another fun thing about all these theorems, just an easy way to check that what you're doing is right, we'll never take the partial derivative and the component location are never going to match up, because it's coming from effectively the curl. So P is never going to have its X partial show up. Q won't ever have its Y partial show up. And similarly, when we look at Stokes' theorem, Z or R isn't going to have its Z partial show up. Just throwing that in there again. So if I compare that to the stuff we've got above, see what we've got. If I want P, that's this first guy right here, Q being the second component in my vector field. First thing I wanted was Q partial X, which is just going to be -7. And I'm going to subtract from that P partial Y, which is just 2. So very, very nice partial derivatives, especially for this double integral we're going to do in a second. Or rather, this double integral that we're not really going to do in a second. We're integrating over our region D because we're moving inside the curve instead of just evaluating along the curve. Still throw a dA in there. And see what we've got. -7 -2. Pretty sure that's -9. If I'm still capable of doing the basic math, which doesn't always work out as well as I'd like. But I just have the double integral of dA. And here's where that last little bit that we mentioned about the problem is going to come in. Because we don't actually know anything about the curve, right? We can't parameterize that curve to try to evaluate its line integral. But what we do know is that our region has an area of 6, which means that the double integral of dA is 6. Because we know if we do the double integral of dA, we just get the area of the region. So that all works out to -9 times 6, which I believe is -54. But again, I've been wrong before. I could be wrong again, but pretty sure I got that one right. I'm sure someone will let me know if I missed. No, but anywho, enough of the easy ones. Let's go look at the next guy. So use Green's theorem to figure out the work done by that field, where we're gonna go along, some curve that we'll outline here in a moment. I'll probably draw ourselves a picture to show what's going on. So yeah, get ourselves a coordinate plane. Don't really need the whole thing, so let me just get rid of some of the negative space. I'll draw that through in a second. So it is asking us to calculate work, which I've already sketched out what the work integral looks like down here. So work as an integral is the line integral of f dot dr, which just so happens to look like the first half of Green's theorem. So if we're saying use Green's theorem to find the work done, probably means that we should be doing the double integral to find that work, rather than doing the line integral right away. So if we just did the line integral, we wouldn't actually be using Green's theorem at all to be calculating that work. We'd just be solving it directly. The whole use Green theorem part is where we actually switch to the double integral instead. But right, let's talk about how this particle is going to be moving. It is going to start at the origin. Excuse me. Right, it's moving particle from the origin, first along the x-axis out to 4, 0. So we're going this way first. Then we're going to move from 4, 0 along the line segment to 0, 4. 0, 4 is that point up there. So we'll be moving along this piece there. Let me just move the point up a little bit. Say that's 4 right here. That's 4 up there. So I moved along the curve this way. And then finally, I'm going to return to the origin from that point. So moving down the curve like this. Right, so that is the curve, that's the path that this particle is going to be taking. And I'm going to be sort of interested in this highlighted green region in here. So down below, I've kind of specified the curve versus the region. C for the curve is just the boundary curve, the path that particle is taking. All that is done in blue. Whereas we're going to be evaluating the double integral over the green region D, because we'll be using the, Green's theorem to evaluate the green area. I'm so sorry. Let's just pretend I didn't say any of that, and go do the rest of the problem. we want to set up the double integral. So let's do that. I need q dx minus p dy, assuming I've set everything else up right. So q dx is going to be y squared minus p dy. I think that's just negative 2x, right? Yeah, this will be negative 2x times 1. We'll color that in purple. And then we'll fill out our bounds in a second as well. I did kind of skip over a step that I should come back and mention here. I haven't talked about it directly yet. It's important when we're setting up Green's theorem and later Stokes' theorem, and I think even the divergence theorem, that we use the correct orientation, because Green's theorem is assuming that we have a positively oriented boundary curve or positively oriented region. And when we say positively oriented, we mean that the path being traversed by this particle is counterclockwise when viewed from above. The right hand rule is oftentimes helpful for determining the correct orientation. Positive is usually up, with negative being down. So if you stick your thumb up in the air so that it's pointed in the positive direction, and then just let your fingers curl, specifically, you need to be using your right hand, which is why it's the right hand rule. So let your fingers curl in the direction that they want to go. That shows you the direction that is positively oriented. So that's counterclockwise when viewed from above. From our perspective, it's trying to turn my hand that way doesn't really work. But from our perspective, this particle is moving counterclockwise. So we do have a positively oriented curve, an important element to bring up here. Cool. So in that sense, that's good. We get to use Green's theorem just directly as it's stated. So that's our double integral part there. And we should also figure out the bounds on our integral. So let's do that. Looking at the lines that make up the boundary of our region, y equals 0 is an easy one. X equals 0 is another easy one. That's the bottom and the left sides. We also need an equation for that line segment that connects 4, 0 to 0, 4. Do you believe that that's going to be y equals 4 minus x? So if I start filling these in, x, which is being integrated second, goes from 0 to 4. Y, the one that gets integrated first, going to go from 0 to 4 minus x. The bottom and the top. So let's take all that and use it to solve this bad boy. I've got some double integral over the region D. I suppose I moved my screen away a little too fast. That looks like it's y squared plus 2x. Y squared plus 2x. Keep dA there for right now because we haven't exactly set up our order of integration yet. I still shouldn't quite pull that all the way. But looking at that double integral, what is it we've got? Still, it's y squared plus 2x. And we're about to do dy first, dx second. Y is going to go from 0 to 4 minus x. And then x is going to go from 0 to 4. So let's integrate this thing. For starters, we'll integrate y. That'll give me a y cubed over 3 plus 2x times y dx. X still from 0 to 4. And then we'll evaluate y from 0 to 4 minus x. If I plug in 0 for y, I just get 0, so that one is easy enough to deal with. this looks like 4 minus x cubed, and 4 minus x also goes in that box. I also just noticed that was y cubed over 3, not y cubed over y. Yep, that all of a sudden didn't look quite right. Then I need to integrate the next thing. I could cube out that binomial, but it sounds rough. I don't want to do it. Instead, I'll just use a u substitution to integrate that thing. U is going to be 4 minus x, du is negative dx. So if I integrate that thing, I ought to get 4 minus x to the 4th power divided by negative 4, or divided by 4 times negative 1, however you like to think about it. There was already an over 3 there, so I'm going to have that be over 12. And again, I should have a negative right there. Plus, if I distribute that 2x through, I'll get 8x minus 2x squared, getting me to 4x squared minus 2 over 3x cubed. Evaluate that thing from 0 to 4. And let's just pretend we did all that work. I got 128 over 3. Yeah, just be careful. Plugging in 0 is going to give you a result because of the way that we integrated our very first term. But conveniently enough, plugging in 4 gets you 0. So, small miracle. Small miracles is the correct quote. I don't know where my head's at tonight. Now, moving on. This thing is labeled quiz 9, because I think this is from when I was going through the course and we had 9 quizzes instead of 8. So ignore the quiz 9 part for now. It's an old quiz question that I pulled in. So let's just treat it like it's a question. Consider the curve done by the parameterization r is 4 cosine t 4 sine t with t from 0 to 2 pi. We want to find the work done by the force field F in moving a particle along C. So remember that the way that these questions are going to be formatted is that we're going to ask you to evaluate, some work function, which is f dot dr, and whichever way we spell out is not the way you should actually solve the question. So we're spelling out a parameterization for r. We're saying find the work done in moving that particle along C, but probably by the way we've asked the question, actually doing that line integral along the parameterization is going to be relatively hard. Whereas if you just switch it over to the other half of Green's theorem, it is relatively easy. And green equals sign for Green's theorem. So I don't want to use that parameterization that they gave me. I instead want to go to Green's theorem and say that I need q partial x minus p partial y. And looking at that field, I mean, those individual components look kind of nasty, but if I just get, q partial x, all I get is negative 4 minus p partial y, all I'm left with is 8. And all of a sudden, this integrand is a lot nicer than I was looking at a second ago. Because yeah, trying to integrate that field with that line parameterization is going to be kind of nasty. I'm going to have like an e to the negative 4 cosine t I got to deal with, or a sine cubed stacked inside a cosine. It gets kind of nasty. Using this other side of Green's theorem means that the work I do is a lot easier. No pun intended. So I've got -12 times the double integral of dA over some region D, which here we should just know something about the region we're integrating over. The last time we saw this problem, it just like straight up told us the area of the region is 6. This time we have to do a little more investigative work for ourselves, but not a super ton. If we come back up and look at the region that we have, we've got a boundary curve C, which is given by the parameterization for cosine t for sine t for t in 0 to 2 pi. At this point, you're probably going to recognize that as a parameterized circle. It's centered at the origin. It has a radius of 4. So if I'm going to be doing the double integral over that region of dA, then it should just be equal to the area of that circle. Area of a circle is pi r squared. So 4 squared is 16. 16 times 12 is 192. It's negative 192 pi. Let's come back up here and make a quick note that in blue, I'm noticing that my radius is 4. Just so I can tie that idea together with a little splash of color. Yeah, well, enough about Green's theorem. Let's go look at surface area. So, what do we want? Set up a double integral that represents the surface area of the paraboloid that lies above the xy plane. And once we're done, we're going to convert it to polar coordinates, it looks like. So we're changing this integral over to r and theta, which makes sense. We have a paraboloid that's there, and it looks pretty elliptical in nature. So I think that polar coordinates is probably going to make the most sense here. Even if they told me to do it in x and y, when I actually did the work, I'd switch it to polar coordinates. So if I talk about what that integrand ought to look like, something has got to go in here, which I'll figure out in a second. But a surface area integral should look like the double integral of ds, where ds is the small shift along the surface of whatever thing we're getting the surface area of. And when we ultimately convert that thing over to cylindrical coordinates, we need to remember to multiply in an r for the Jacobian. So I'm just going to write that down right now before I forget about it. But let's go talk about the thing that we should be integrating. That thing is the magnitude of the normal vector. And that normal vector looks like negative z partial x, negative z partial y, and z partial z, which is just 1. And I want the magnitude of that thing, which looks like the square root of z partial x squared plus z partial y squared plus 1 squared. Kind of add some color back in, make that one purple, make that one yellow. Might as well make that one pink. So that is the thing that we are looking. That is the thing we're looking to compute, this square root. Since we have a scalar function here, we know we're looking to compute the double integral of some magnitude of a vector. Instead of if our surface were described by a vector valued function instead, we just take the dot product of that surface with a different vector. Here we need the magnitude. We need the magnitude of this of this vector. So if we go computing that, this is going to look like negative 6x squared plus negative 6y squared plus 1, right, where I'm getting all of that from my function z equals 16 minus 3x squared minus 3y squared. Derivative of negative 3x squared is negative 6x. Negative 3y squared is negative 3y. And here, and here, and here's where I'll just switching things over to polar coordinates. Because I've got 36x squared plus 36x squared plus 36y squared. There we go. Is just 36r squared. 36r squared. Don't forget the plus 1 that's still in there. All right. So this whole shebang is what is going to turn into our integrand. And now we want to get the double integral of this thing. Burp. So let's start writing down what that looks like. It is going to be the surface area. Well, first off, just continue making some notes for myself. dA is r dr d theta. Mark that one in red so we can see why that red r keeps showing up. So now that I've got dA sorted, calculate this area. The surface area. It is a double integral of that square root thing that we just did a second ago. And we'll find our bounds once we're done writing it all down. So this was 36r squared, 36r squared plus 1 times r. And let's do dr d theta, where theta is the easy one. It's just from 0 to 2 pi. Right, we've got nothing to stop us going all the way around our circle. Our paraboloid's going all the way through. We aren't told like specifically it's going to be in like the first octant or something odd like that, first quadrant or the top half. No limits on a particular section of the graph we're looking at. So theta will just use its default option of 0 to 2 pi. So now it's the other guy that we have to figure out. Our bounds on R. So let's talk about what its bounds ought to look like. I'll need a little bit of space over here. We want this paraboloid to be above the xy plane, which means we're going to want to look at a projection of that paraboloid into the xy plane. In particular, I think it'll make sense to look at the intersection between the paraboloid and the xy plane. That intersection is the plane z equals 0, because that is the xy plane, and it's equal to 16 minus 3r squared. Just go ahead and simplify that for ourselves right now. So we've got to find a solution for r here. I think we can see that if I just add 3r squared over to the left side, divide by 3, take a square root, r should be the square root of 16 over 3, which we can simplify slightly, call it 4 divided by square root 3. Technically, we'd need a plus or minus here, but let's just stick with positive values for r in this integral. If we let the negative values in, we'd have to go think about theta again, and it was easier just to call it a full circle. All right, so R should start from its middle or its default value of 0 and go out to a maximum value of 4 square root 3. And now I think we're ready to just solve this thing. So let's talk about evaluating this integral. It is a separable integral, which is really nice. Since I've got a function of theta alone multiplied by a function of r alone. So the integral of d theta from 0 to 2 pi is just 2 pi. Handy shortcut. Cuts out on a lot of extra work. I am going to need a u substitution in order to integrate the square root of 36r squared plus 1. So 36r squared plus 1 will be u. That means du is going to be 72r. I already have the r dr on the outside. The part that's missing is 1 over 72. Or rather, the part that's missing is 72. I wanted 72 RDR. I had 1 RDR. So I'll multiply 1 over 72 over 72 in, leaving me with a leftover 1 over 72 that I'm not spending in order to make that integral happen. Then I'm integrating a square root. I'm integrating a 1/2 power, which is going to go to a 3/2 power. And then I'll have to divide by 3/2 or multiply by 2/3. So I'll throw that factor in. And now let's have a big parenthesis for the actual evaluation of this integral. So I've got 36 r squared plus 1 raised to the 3/2 power. And I need to plug in 4 divided by the square root of 3. And then subtract from that whatever I get when I plug in 0 for r. Plugging in 0 for r is going to be particularly nice because 36 times 0 squared is 0. So the only bit that's left over is 1, and 1 to the 3/2 is still 1. And I don't want to mess with that number anymore. That's good enough. That's good enough for me, I think. I can at least see where all the numbers came from. If you need to type a number into an exam, you just plug all this into a calculator. But if we're looking at some partial credit on this problem, if I see this line right here, I'm just going to stop right there and give full points. I don't want to investigate further than this line. That looks rough. So I'm going to leave it right there. And now on to our next super favorite problem. Stokes theorem. Did greens? Now we'll do Stokes theorem. After this, you can probably surmise we're going to look at the divergence theorem. Those are the big Andes right now. So it says here, we should use Stokes theorem to evaluate the double integral of the curl.ds. And that integral, as it stands, as long as we have a positively oriented curve, that is one side of the Stokes theorem equation. So if we're saying use Stokes theorem to evaluate this double integral, you should immediately think in your head, don't actually do the double integral. Instead, switch to the line integral and do that. So the line integral over our boundary curve C of f dot dr. Because if we're saying use Stokes theorem or use Green's theorem to do something, the math that you actually want to do is the other side. Because probably that means computing the double integral itself is going to get messy. So let's take a look at what we got. We know our field is F right here. And what do we want? If we're not going to do the double integral, we aren't going to need the curl of that thing, but we are going to need to parameterize the boundary. So to go look at where that boundary is going to be, probably want to highlight this spot right here. Z is greater than or equal to 0. So we're looking at the top half of a sphere. In fact, we're looking at the top half of the unit sphere, because looking at the equation that's right next to that, x squared plus y squared plus z squared. That's the sphere with a radius of 1 centered at the origin, or lovingly named the unit sphere. And it's oriented upwards, is the other part that we get there. So if it's got upward orientation, that is the positive direction, generally speaking. We usually say up is positive, down is negative. So if it's got upwards positive orientation, then the hemisphere of the curve should be traversed blank when viewed from above. And if you click that drop-down arrow, your two options in blank are clockwise and counterclockwise. And since we've already got this thing oriented in its positive direction, we should use the positive traversal, being counterclockwise. If we were told it had negative orientation, then we'd use the negative traversal. So we'd go clockwise instead of counterclockwise for negative. But I'm getting out ahead of myself. Counterclockwise is our positive traversal. So that's the one we want. So if I'm talking about that boundary curve, I know that my surface is the hemisphere, the part where z is greater than or equal to 0. But if that's my hemisphere, I'm cutting it in half right through the center with a horizontal plane. Right there is the motion I'm doing. I'll put it on the camera. So that means that the boundary curve is the part where z is equal to 0. So I'm going to come and fill that in right here. Since it's asking for the boundary curve r of t in those three blanks, the boundary curve is where z is equal to 0. So I'm going to fill that in for z. I know that t needs to go between 0 and 2 pi. And I need to finish off my parameterization for the y component. If x is going to take on the role of cosine, then y is going to need to take on the role of sine. This should be sine t, specifically 1 times sine t, which I'm going to write in just to, get you thinking about the correct parameterization. The radius of the sphere would be important. If we, if that were x squared plus y squared z squared equals 4 instead of 1, then I'd have 2 cosine t and 2 sine t. But you probably knew that this far in. So let's go use this parameterization. And I'm going to run out of space if I try to write it inside that webwork box. So I'm going to use the space I provided myself below. All right, let's bring back f. If I think about all the stuff that I want here, I'm looking to do the line integral of f dot dr, because that's actually using Stokes' theorem, which means I'm going to need dr. Or in other words, I'm going to need r prime of t. So I can just take its partial derivatives right down the line. Derivative of cosine is negative sine. And the derivative of sine is cosine. And conveniently enough, the derivative of 0 is 0. All right, let's take that into some value over here. So the thing that it asked us to calculate was the double integral of the curl of f dot ds. But because we're just so smart and allergic to doing more work than is required, we're going to say, hey, it's way easier to instead do a line integral of f dot dr, and that's the thing that we just spent the last little bit figuring out. We know that t is going to go between 0 and 2 pi. right? We had that from back up here on the top of the screen. And we need big F dot dr. So let's go back and look at big F one more time. It's the part that's highlighted at the top of the screen. Let's try again. 7y cosine z, 2e to the x sine z, and 3x e to the y. So bring that back down here and plug in the stuff that we had for x, y, and z. X is cosine t, y is sine t, z is 0. So going right down the line, we had 7y times z, so that's 7 sine of t times 1, right? Because it was 7y times cosine z. I think I forgot the cosine when I read it off a second ago. I don't know why I'm not just zooming out so I can put it all on screen at once. That's way smarter. There we go. 7y times cosine z. Z is 0, so cosine of 0 is 1. Next up, 2e to the x times the sine of z. Again, z being equal to 0. Sine of 0 is 0, which means we multiplied the whole thing by 0. So that part's gone. And if you were looking ahead, you might recognize that this next part of the parameterization is not important, but I'm going to do it anyway as an exercise. Filling in the final bit, 3x e to the y. This is 3 cosine t e to the sine t. Which writing that out has me a little worried because it looks like something I don't really want to integrate. Wouldn't be that bad, I guess. View is sine t. I've got a good du substitution. But if I didn't have to, I'd rather not. I need to multiply that thing by dr. Conveniently, dr, it's already solved. It's up here. I'm going to copy and paste it and bring it right down here. That's my dr. Or rather, that's my r prime. I am still missing one rather important element of dr, and that's the dt. Dr is that vector multiplied by dt. And the super duper fun thing about the dot product of those two vectors is that only the x component is non-zero. The y component is 0, the z component 0. The only thing I get left with is negative 7 sine squared of t dt. Mark that in green again. And we're integrating from 0 to 2 pi. And I know that the integral of sine squared dt from 0 to 2 pi is just pi. And I'm done. Except I'm not going to be done because I'm going to explain that a bit more. I was hoping I left myself notes already here, but I hadn't. Because I'm sure that there are going to be some questions out there of, wait, what? How'd you know that was just pi? It is a shortcut that one that I very much appreciate. I use it quite a bit because of how often we end up integrating sine squared or cosine squared over a good chunk of its period. And so I want to talk about why I know that's pi, or maybe why I remember that's pi. So I'm going to paste in some work here that you might have remembered if you've seen it in my notes somewhere else. Because I know I posted it somewhere. Just can't remember where exactly right now. Okay, this part in gray. Oh, cool. It showed up. Love that for me. All right. So this part that I just pasted in, remembering what the integral of sine squared or cosine squared is equal to. And it helps to think about the graph. So I want to start by just looking at the graph that's down here, the graph of sine squared as it all comes together. So sine squared has that dark gray line through the middle. You can see it going there. Looks not too dissimilar to the sine wave itself, just with only positive sections, because sine squared is an only positive function. Sine squared is an even function. But I also know that sine squared plus cosine squared is equal to 1. So if I add sine squared and cosine squared on top of each other, I just get 1 the whole way through. Meaning, looking at sine squared and cosine squared stacked on top of each other, I should just get a rectangle with a height of 1 and a length or a base, a width, whichever word you want to use for the other side of a rectangle. That's however long I've made the rectangle stretch along the x-axis. In particular, I like looking at 0 to 2 pi because it's one full cycle. So I know the area of that rectangle. It's got a height of 1. It's got a base of 2 pi. Base times height, 1 times 2 pi, 2 pi. Cool. Area of the rectangle is really easy to calculate. The next thing I want to posit here is that sine squared and cosine squared over their whole period must cover the same amount of area. The area must be evenly split between the two of them, since sine and cosine both come from the exact same wave function. So as long as I go over a full period, I know that the area should be split evenly between the two. So sine squared and cosine squared each need to make up half of the area, as long as I'm integrating out to a nice number. So every time I integrate through a full quadrant, I know that idea holds up. So if I'm integrating over 2 pi, I know that sine squared is exactly half of that rectangle, and half of 2 pi is pi. And again, this trick only works if I'm integrating out to a few specific angles, but really any multiple of pi over 2, and this symmetry holds. Because as long as I'm integrating over a full quadrant or a full integer number of quadrants, I can use this principle to solve the integral pretty easily. Just use an area argument instead of integrating directly. Because the other option is I could use a double angle formula to bring some stuff in and integrate it out that way. But honestly, that's a bit of a pain. I know you're going to be pressed for time on the final exam. So this trick is one that I think is quite helpful. Lets you skip over some of the more tedious math to just jump straight to an answer. So hopefully you found that helpful. I know it's something I use quite a bit when I'm doing some of these problems. All right, another Stokes theorem problem. I put a star by this one, so I must have thought it was really important. So let's go look at why I thought it was going to be important. We want to use Stokes theorem to evaluate f dot dr, where f is this field and c is a triangle with a bunch of vertices. Oriented counterclockwise is viewed from above. Okay. There's a whole bunch of stuff going on. But let's talk about what we know. Stuff that we've said definitely should make sense based on the way that we know these problems are going to be asked. The problem said I should evaluate f dot dr, the single integral of f dot dr, so the line integral along the boundary curve. Since the problem told me to do that, I know that's the integral I'm definitely not going to do. Told me to do the line integral, so I'm already thinking in my head, okay, I should actually do the work for the double integral version, because otherwise I haven't actually used Stokes' theorem. So I'm already getting into the headspace where I want a double integral going. If that's the case, I'm going to need the curl of f here. And I'm also going to need a normal vector. That's the other part that I'm going to need off of. It's the other part that I'm going to need off of Stokes' theorem. I don't suppose I wrote any of the work down already for myself, did I? Nope. Okay. So let me just move down to some space where I can write all that in. So we'll just start with writing down what Stokes' theorem is, because I think that's a pretty good idea. F.dr. They asked me to calculate this, so I'm actually going to calculate a double integral over a surface, switching from the curve C to the surface S of curl of F dot ds, where F and ds are both vector values. And I'm going to change that around even one more time. Call this the double integral over a surface S of the curl of F dotted with, instead of just some vector ds, I want to call that a normal vector times a scalar valued ds. To just emphasize again to myself that when I'm doing that surface integral half of Stokes' theorem, it's the curl dotted with some kind of normal vector. So the two elements that I really want to do, the surface integral side of Stokes' theorem, the curl, which obviously I can calculate, but the normal vector ends up being the spot, the thing that I need to remember to calculate. So I need to find a normal vector. Let's come back up to the top. So I'm going to need to find a normal vector of the surface that I'm going after. And my surface here, or our surface, let's be, a little bit, a bit of a community about this. This is our surface. I've got it's a triangle that's being created here, but a triangle is just some section of a plane. So I want to put these 3 points together to find the equation of a plane. There are a few different ways I can go about solving for this thing. What is the best way to get at that? Ultimately, I'm just after the normal vector. If you've gotten comfortable enough with visualizing these spaces, you might be able to look at these 3 points and immediately conclude that your normal vector is 1, 1, 1. If that works for you, great, awesome. Skip to n equals 1, 1, 1 and move on. But I'll be going over a bit more of like how I would have arrived at that conclusion, instead of just magically knowing that my normal vector is all ones. So another way you might go about it, since I've got the point 3, 0, 0, 0, 3, 0, and 0, 0, 3, you might also jump to, okay, this would just be like x plus y plus z equals 3. Also totally a valid way to get that plane. If you see that, awesome, great. Enjoy spending a little less time on this problem. But if none of that made any sense and you're completely lost on where I'm pulling these numbers from, let's go over a more systematic way to get the answer. So I am going to start from 3, 0, 0, and I am going to get vectors that point to the other 2 points. So if I go, am I doing that right? My first vector, 3, 0, negative 3. My second vector is going to be 3, negative 3, 0. Right? What I really need to do is I need to connect one of these points to the other 2 using a vector. And this is the This is the option I chose to use. So I guess I'm doing A minus C and A minus B if my points are A, B, and C. Yep. Did I parameterize the thing all right? I think so. But anyway, I'm going to need a cross product of these two things. So if I run through that real quick, 0 times 0, 0 times 0 minus. Oh, you know what's happened? I think I just have my notes are a little backwards. And that's why it's not. Yeah, okay. All right, hang on. Let me reorganize these. Something wasn't making a ton of sense here. I mean, that would have worked to have done that guy. But let's just pretend we actually did this one. This one makes more sense anyway. So that's the vector AB cross the vector AC. AB cross AC. Or maybe it's BA cross CA. Either way. If I do this cross product here, -3 times -3 is 9. Minus 0 is still 9. Up next, 0 times 3 is 0. Minus 3 times -3 is 9. And one more time. What do we have? We have 3 times 0 minus 3 times -3 is 9 again. So 999. That's my normal vector. So I'll turn that into a plane by just plugging in a point. Let's move A, B. Is there space for that? How about up here? It's a little bit hard to see, but I know I'm going to need the space down here. AB and AC. I want the vector. 9 times x minus 0. 9 times x minus 0. Plus 9 times y minus 0. Plus 9 times z minus 3 is all equal to 0. That's the equation of my plane. I use the point 0, 0, 3 to create it. I can divide everything by 9 to get rid of all of those. I'd come up with the remaining equation is z equals 3 minus x minus y. And turn that into a normal vector. So my normal vector is negative. Let's try again. Negative z partial x. Negative z partial y. And 1. So I'll comment on again in a minute. Which looks like negative. -1. Negative. -1 again. And 1, which by the end is the vector 1, 1, 1. So that got me to a normal vector. So remembering the way that normal vector works, I'm sure it'll be written down somewhere. Remember that the final exam is open note. So you can have these notes available so you can flip to the page to find where that formula is. The way I usually remember normal vectors is that if I had put x, y, and z all on one side of the equal sign and then taken each partial derivative, that's what should go into the normal vector. But whenever I take the partial derivative of z itself, I just get 1. And since x and y should be on the same side as z, but we usually express it as z equals some function of the other two, x and y as they stand are on the wrong side of the equal sign, which is why they get negatives in the formula. This is just one of many normal vectors. So we need to take a moment to make sure that we have the correct normal vector. Let's come back up to the information we were given. Do one more check here. We're told that this curve is oriented clockwise, or excuse me, this curve is oriented counterclockwise as viewed from above, right? I'm looking right here. I see counterclockwise as viewed from above. Both of those words are important. Both of those mean that this thing has positive orientation. So the other, important question that's been asked, since the triangle is oriented counterclockwise as viewed from above, the surface we attached to this triangle is oriented. Our options are upwards or downwards. We have the positive orientation already, so we want the upward oriented surface. Surface should be oriented upwards, which means the normal vector that we get should point upward. Here we're defining up and down using the z direction. So positive z is up and negative z is down. So we want the normal vector that has a positive 1 in the z component, or any normal vector that has a positive z component is an upwardly oriented normal vector. Just to illustrate a point, if we had switched this thing up to say that we wanted a downward oriented surface, so a downward oriented normal vector, we would have used this slightly different equation for the normal vector. So this is if clockwise and downward, where the parts in question for looking at it being downward is the -1 in the z component, the negative in the z component of the normal vector. So we'll just want to pay attention to that piece right there, decide if it should be up or down. But again, we wanted the upward one, so we'll use 1, 1, 1 as our normal vector. We're gonna, now that we have that normal vector, spend some time trying to get it, but we got it now, so let's put it to use. We want to use that along with the curl of our field to get an answer. So I'm going to just add some color up here again. P, Q, and R. I'm going to want to go get the curl of that thing. So curl of F, if I run through the pieces, I start from R and then work my way backwards twice, taking partial derivatives as I go, making sure never to take the partial derivative of the position that I'm in. So it must start with R partial Y, which is 0, minus Q partial Z, which is 2Z. Then into P partial Z, which is 0 again, minus back around to R partial X, I get 2X. Then Q partial X is next. Again, that part is 0, minus, last but not least, P partial Y, it's 2Y. And that's my curl. I suppose I'll simplify this a bit. It is negative, let's try again, negative 2Z, negative 2X, negative 2Y. All right. And we finally have all the pieces that we needed. We can go compute this integral after a good chunk of work. Let's do that. We're going to look at the double integral over D, because now we're switching over to the region D instead of the surface S, because we'll be projecting this thing down into the xy plane. Curl of F, we wrote it down a second ago, negative 2z, negative 2x, negative 2y. But we're also going to use the substitution z equals 3 minus x minus y. Since we found that that was the equation of our plane, was 3 minus x minus y. This is negative 2x, this is negative 2y. We're going to dot that thing with 1, 1, 1. 1, 1, 1. dA. Add an extra splash of color right there. Again, to highlight the fact that we were wanting the upward pointing normal vector. So we wanted to make sure that the z component of our normal vector was positive. And then simplify that dot product. Nice thing about all that, it's just negative 6. So this is the double integral over the region D of negative 6 dA. And that's going to be pretty easy to compute. This is negative 6 times the area of a triangle. It's 1/2 base times height. All 3 dimensions had a length of 3. So x goes from 0 to 3, y goes from 0 to 3. That triangle is 1/2 times 3 times 3. Multiply that by negative 6. And I get negative 27 when all is said and done. Woohoo! Cool. So that's one whole Stokes theorem problem. I think like that problem alone, I wasn't paying attention at the time, and probably it's better if I don't. But that problem takes a minute. But in the end, it was all worth it. All right. So a question that came up: does the normal vector not have to be a unit vector? Because as you might have noticed, we didn't use a unit vector here when we calculated that thing. And the best answer is that, the correct answer, no. This normal vector does not have to be a unit vector when we set it all up. The reason for that being that if we were to calculate a unit vector here, like the unit normal vector, let me back up and try again. The reason we end up not needing a unit normal vector in Stokes' theorem is by when we look up here at n times ds. That part in green at the top of our, no, not at the top of the screen right now. Looking at the wrong screen. There it is. It is, yeah. This n times ds at the top of the screen. That ds has baked into it a magnitude of the normal vector that we're using. So ds as a scalar is the magnitude of the normal vector times dA. And converting to a unit vector means that I would take my regular vector n and divide it by its magnitude. So I have a magnitude of the unit vector that was built into the denominator from the calculation of the unit vector itself, and I have a magnitude of the unit vector baked into ds that goes into the numerator. So when I simplify that down to dA, those two magnitudes end up canceling out. Because again, one in the numerator, one's in the denominator, which means that any normal vector will do. because its magnitude will show up twice, once in the numerator of ds and once in the denominator of the unit vector. So yeah, just a regular normal vector is fine. Or just a regular, just a regular normal vector is fine. It does not need to be a unit vector. Hopefully I managed to string together some coherent sentences there. Cool. Let's go look at the next one. The divergence theorem. So what does it want here? Use the divergence theorem to calculate the outward flux across the surface of a solid bounded by a bunch of stuff. So I'll take a moment to remind ourselves that flux is a surface integral, right? Because if we're calculating flux, we're looking at some field passing through a barrier. Meaning, question is telling us to calculate a surface integral. So we're going to be smarter than that and use the divergence theorem to calculate a triple integral instead. So we always want to do the opposite of whatever the problem tells us. Hopefully I've said that enough by this point in the video. So cool. Let's go do some things. What do we want to start by doing? Maybe figuring out what our solid looks like. So at its most basic, the solid is a cylinder. It's y squared plus z squared equals 25. So this cylinder is expanding along the x-axis. Its cross sections are going to be circles that are parallel to the YZ plane. Yep. So it's getting long along the x-axis. So if we just start filling some stuff in, probably we won't end up using these bounds ultimately, but we'll just pretend like it's the Webwork problem and fill them in. X we know goes from 0 to 4, so that's just going to be a real easy 0 to 4. Y and Z, well, I'm looking at circles with a radius of 20, with a radius of 5, so it's just a matter of which one I'm supposed to do first. If I look at my order, it's Z, then Y, then X. So I should do Z first. Solving that thing around, I'm going to get both the positive and negative square root of 25 minus y squared for the Z bounds. Probably we're going to end up converting this thing to cylindrical coordinates, but that's a step ahead of ourselves. Then y just needs to go between its minimum and maximum value, which is -5 and 5. So again, I'm using this cylinder equation right here to get both of those values, or both of those bounds, and I'm using the x bounds, or the x surfaces, to come get the x bounds. And since this thing is the divergence theorem, I'm probably going to want the divergence of something. So let's go get it. The divergence of f is the dot product of the del operator with our field, which just means take the partial derivatives one at a time and add them up. So first term, partial derivative with respect to x, is going to be 6y squared plus partial derivative of the second term with respect to y, 2x e to the z. There's no y in there, so its partial is 0, plus the third piece, its derivative with respect to z, 2z cubed, its derivative 6z. So this whole line right here, I said this whole thing, said this whole line right here, that guy, I am going to take it and put it in that box back up at the top. That's where it goes. So that'd be, answering the specifics of this problem, but then it says find the actual flux across the surface S, which will just do a triple integral through the solid. And since I knew that that last one was going to take a while, figured I'd give us a break by computing this integral ahead of time and then just walking through it. So again, the flux is a surface integral. That is its definition. And it's also the flux is going over a closed surface S, which is why I've put that circle around the double integral sign. So right there at the very beginning, upper left corner, I suppose I should be just marking some stuff as I go. I'm, starting up here at this point. Looking at the calculating the flux as a double integral or a surface integral, but we're going to use the divergence theorem to change that to a triple integral instead. They told us do a double integral, so we're smarter than that. We're going to do a triple integral. So we'll show them. Them, I guess, kind of being me in this case, but don't worry about that. Cool. Triple integral of the divergence over the solid E. We'd calculated the bounds that are here in the top line. I didn't want to write them all in because I knew I wasn't going to use them. So I just had some scribble marks in the correct color. And I brought my divergence back down. I just want the triple integral of the divergence. I can see this thing would be way better to integrate in cylindrical coordinates, since they even straight up told us that we're integrating a cylinder. So let's make that change. Big difference between how we would normally calculate this stuff is that because our cylinder is expanding along the x-axis, I'm going to use x as my third variable instead of z. So that means that I'm going to be putting r and theta into the yz plane instead of the xy plane. I'll use y equals r cosine theta. I'll use z equals r sine theta. This could theoretically be backwards and still work out, but I think this substitution makes more sense, or this parameterization makes more sense. It doesn't actually matter either way here because we don't end up having to do any real integration with theta. We only have to integrate d theta. But in the end, after switching this thing over to cylindrical coordinates, I'm just going to end up I'm just going to integrate 6r cubed. 6r squared comes from the divergence, and then don't forget about an r from the Jacobian for dv. So if I look at my bounds for all of that, I knew I wasn't changing x, right? I'm not changing x over here. So it still goes from 0 to 4, just like it did previously. You can see I was so focused on the integration part, I'd forgotten the part where I highlighted in pink the substitutions that I was using for x and y and z. But yeah, the substitutions are over there on the left. Maybe you saw that the whole time I was talking about it. I had completely blanked that out. Yeah, big highlighted thing. I'm good at this stuff. Right, we're gonna integrate all the way around our axis. So theta, I'll just have it standard 0 to 2 pi. There's nothing where we're only going to take half of the cylinder or only the first octant or something weird like that. We want the whole thing, so 0 to 2 pi. And our circle had a radius of 5. So r goes from 0 to 5. Crunch some numbers. I got 7,500 pi. Right, 4 for the x integral, 2 pi for the theta integral, and then 6 times 5 to the 4th divided by 4. Yeah, that's the number I came up with. 12 pi times 5 to the 4th is 7,500 times pi. Nope, and it looks like I left myself one last problem. at least where we're gonna set up the top part. And maybe we'll look at the rest. So one more divergence theorem problem. And then I think I'll talk about some generalities, hopefully hit some, true false style problem, or at least that's the dream. So let's take a look at what we got. This first one says verify that the divergence theorem is true for the vector field provided the solid region E, which is bounded by the paraboloid given in the xy plane. So when we say verify the divergence theorem, this problem is going to make us solve both sides just to show that it all works out. And I'm going to compute the easy side live because it won't be too painful. But then I'm going to talk about the less easy side with the work already done. So I think it'll be easier to just kind of talk about it in generality and then being able to wave our hands and say that the math is done, knowing that we could do the math if we really had to, but as long as we don't really have to, let's not. So we need the divergence of this field right up here at the top. I'll zoom in a bit so I can write a bit more clearly. If I just take some derivatives right down the line, I'm looking at 4x plus 2x plus 3. Or 6x plus 3 if I simplify. So I know that once I have the divergence, I can just plug that into the integrand because that's all I needed. Divergence theorem, at least the triple integral side, is pretty nice and straightforward. Next, I should go figure out what my bounds are. So I need to create bounds on this here solid. We're going to go in order from z to y to x. So just reverse alphabetical order for our bounds of integration. And let's see what we get. We should start with z though, because it was the first one. We're bounded by the paraboloid in the xy plane. That paraboloid is above that xy plane. So the lower bound will be 0, and the upper bound is the thing that's right there. 25, there we go. Minus x squared minus y squared. And I can see again that I'm probably not going to do this integral in Cartesian or rectangular coordinates. Looks like a really good option for cylindrical coordinates again. I can see that z is done up nicely, but the rest of it looks like circles. And if it looks like circles, I probably want cylindrical or spherical coordinates. And since z is nice, I'll use cylindrical coordinates. But just to humor WebWork and fill in the bounds that it's going to ask for, y is next. So it's plus or minus the square root of 25 minus x squared. And then finally for x, I can just do negative 5 to 5. Cool. So that is all of that. All done. So let's go calculate this integral. Oh, hey, look, I did it already. I thought I had actually left myself this step, but apparently not. Cool. So I'm just going to do the triple integral of 6x plus 3 times dv. And like I was saying, or maybe muttering to myself as I was going through the process, I knew I was going to want to switch this thing to cylindrical coordinates. So that's what I did here. We'll do z first, 0 to 25 minus r squared. But then r and theta, circle with a radius of 5. I'm doing the whole circle. So 0 to 2 pi for theta, 0 to 5 for r. And I just did that up already. I got 3 pi times 25 squared all over 2. So I'll just come fill that into this box right here. 3 pi times 25 squared divided by 2. So that was the first half of the divergence theorem. The nice half, I think. Oftentimes that triple integral is a lot nicer than a surface integral. But just to look at it, one time to say that we did, let's go through the ugly process of computing the flux out of that solid directly rather than using the divergence theorem. And hopefully this will give us a good argument for continuing to use the divergence theorem, because it's going to look ugly. So what do we want to consider here? We're going to say that our surface S is the union of a paraboloid and a disk. So the paraboloid being the one that we were describing earlier. It's 25, z equals 25 minus x squared minus y squared. And the disk is going to be the flat, thin disk that's in the xy plane. So that effectively our solid is made up of a paraboloid that runs into the xy plane. There's a circle down there. The disk is just the bottom of our solid. So consider the surface S, which is P union D. P is the paraboloid, D is the disk. We picked some nice letters. Hooray for us. I've put a star up there and I've filled in some of the answers already, but maybe let's just go through the process. Because I'm going to use a shortcut in the end to get to our answer finally. But if I'm going to compute the flux, I'm going to need curl dot ds for both of these things, which I'm going to represent as dp and dd, just so that I can differentiate my two surfaces, the paraboloid and the disk. So I'll start by coming up with what this paraboloid looks like. So I've got my field, it was 2x squared, 2xy, 3z, and along the paraboloid, I'm going to use the parameterization that z is equal to 25 minus x squared minus y squared. I know I'm going to need a parameterization because I'm moving into surface integral territory. I'm doing a double integral. So I need to parameterize my shape to only have two variables. Quite often, the number of integrals we take corresponds to the number of variables we're allowed to have. It's a surface integral, which is two integrals, so I only get two variables, meaning I need a parameterization. Fortunately, we have our parameterization is spelled out for us. We already have z equals something. I'm just going to use it. So that means that our parameterization is that r that I've written down there, and it's highlighted in bright hot pink. But this is my parameterization right here. X, y, 25 minus x squared minus y squared. I need to figure out dp, which means I need a normal vector. That normal vector is going to come from the cross product of the partial derivative of my parameterization with respect to x and y. So I've got those two partials there, took the cross product, I got 2x, 2y, 1, meaning that I could have, that I think is the best way to think about getting your normal vector, is that it's the cross product of two partial derivative vectors, but we can always use a shortcut. That's the thing highlighted in green down here. dp is negative gx, negative gy1, where this thing is, we want it to be the outward normal vector. So I'm going to use positive 1 because the upward direction is going to be outward. I think I've sketched myself a shape over here. Indeed, I have. So this is what our shape looks like. I maybe should have started with this earlier, but I don't know. It's here in the notes. So we're getting to it now. This is what our shape looks like. The blue section's the paraboloid. The red section is the disk. I want the outward flux because we're looking at the flux that goes out of this solid. And when we are along the paraboloid, outward is up. right? All of those normal vectors, everything that comes out of the paraboloid is going up, whereas everything that comes out of the disk is pointed down. So when I'm calculating my normal vector for the paraboloid, I want to make sure that I have a positive z value. But when I'm calculating my outward normal vector for the disk, I need to make sure I have a negative z value. So outward ends up being a bit tricky sometimes. Oftentimes outward is going to switch between up and down depending on where in the solid we're investigating, or where along the surface of the solid we're investigating. So I left myself a star earlier, right? I said that, trying to look at the integrand for the surface integral along the paraboloid, just because I didn't want to rewrite the whole dang thing. It's a star right here. It's all of that. We're supposed to calculate a double integral of that thing. It's gonna be rough. That's why we're running through this one quick. Quick is sort of a relative term, if you'll allow me. But right, so then let's come back and look at the disk. We need a normal vector for the disk. Again, needed to make sure that our normal vector pointed down, which is why we have positive gx, positive gy, -1, or 0, 0, 1. When we look at our parameterization for the disk, it's the surface z equals 0, because we're in the xy plane. So that parameterization is z equals 0. So the whole parameterization together is just x, y, 0. Granted, it is a circle, but we'll use some bounds to contain that later. Cool. So our surface is described by x, y, 0. And that means that its normal vector is 0, 0, -1. If we take the dot product of that with the field, which is 2x squared, 2xy, 3z, substitute in what we know for z, which is 0, dot product of that whole thing is 0. Cool. So there's no flux coming out of the disk, which is kind of nice. So my two integrands, I know what they are now. The star for the top one, 0 for the next one. And here's where I just really didn't want to do the math to figure out the actual surface integral along that paraboloid, because it looked like a bear. So instead, I'm going to use a trick to evaluate that surface integral. I know that the surface integral over the entire surface, that's the boundary of that solid, is going to be equal to the triple integral we calculated first. That's the divergence theorem. It tells me that those two things are equal. I also know that the total flux out of this surface is equal to the flux through the individual surfaces all added up. I was able to express my whole surface as the union of two separate surfaces, a paraboloid and a disk. So I know if I add those two pieces together, if I add P and D together, I should get the entire surface. And that entire surface is equal to the triple integral over the solid E, which means P plus D is equal to E. Blue plus red is equal to green, if you're following my color along here. So if I just want to get blue, P, by itself, I could subtract D to the other side and solve for it that way. And that's going to be, to my mind, the easiest way to actually evaluate this specific surface integral, is to say it's the triple integral of the divergence minus the flux that we lose out of the disk. So the green integral minus the red integral is equal to the blue integral. I've said integral too many times. Hopefully I've said it right every time, but I don't know. Who knows? Whew. I've been talking for a while. All right. So I think that's the last problem that I had set up for us to do. Wait, why have I put this one here? Do I really want to do one more? Oh, I did. I'm going to fill this one in later. I've got the work done up already somewhere. So actually, you know what? Let's do it like this. I can just come over here, grab this, and if you'll allow me, come back over to where we are right now. I'll get rid of that guy and paste it back in. Oh no. What have I done? Oh, that's all that happened. All right. Here it comes back in. Here's all the work that I would have done if we had done it together. We'd done one similar to this already, so I'm just gonna let this one go. But it's telling us to use Stokes' theorem to evaluate a line integral, so we know we're gonna want to switch it over to a double integral, and we'll knock ourselves out again. Go figure out a normal vector, figure out a curl, take the dot product. Turns out we only have to do the double integral of 15, which meant that this ended up being extraordinarily nice. Since the normal vector to our surface, which is in the plane z equals 3, is just the vector 0, 0, 1. That's not the one I really wanted to talk about. I think the rest of it when I was really into. So we hadn't really talked about this kind of looks like an integral in spherical coordinates. So I think the main value in looking at this one was recognizing when to parameterize something using spherical coordinates in some of these later chapters. So it started providing us with a parameterization down to just 2 variables, because we're going to do a surface integral. But the first value is cosine t times sine s. And when I see those two together, I immediately start thinking about spherical coordinates. Since a couple of our variables in spherical coordinates end up being the product of 2 trig functions with different angles. So I see a cosine and a sine, they have different angles in there. So instead of having to go through all of the pain of trying to parameterize from knowing what x is, I'm just going to rely on the fact that I already know what spherical coordinates look like and use that parameterization. So t is going to be theta, s is going to be phi. I just fill the rest in, which also means that I'm going to have a, my ds value should look like rho squared sine phi d theta d phi, where I can see that my rho, my radius is 1 because I'm only looking along the surface rather than all the way through the solid. So I'm only looking along the edge. So I'll plug in 1 for my radius, and s is taking the place of phi. So I've got sine s in for sine phi. Also, if I look at some other things going on here, I'm oriented in the direction of the positive y-axis, specifically with y being greater than or equal to 0. So I'm only taking positive values for y. So x and y are the 2 variables that are described using theta. So if I'm taking specifically positive values for y, that means I'm talking about the first and second quadrants. And if I'm thinking, go back to the unit circle, the first 2 quadrants is everything for theta between 0 and pi. So I am limiting my theta integral this time because I was told to specifically take only the top half of the circle, or only the right half of this hemisphere. So again, that right half corresponds to 0 to pi. But that's mostly what I wanted to say about this guy. There's some extra work if you wanted to finish it out. And this last one, since I do believe this will be the last problem that we'll look at here as a group in these exam reviews. Honestly, I just kind of am partial to this problem. This one looks absolutely insane when you do it all the way up. If I had shown you this problem when you came into the beginning of Calc 3, fresh out of Calc 2, just showed you this and said, by the end of the semester, like, this is the math you're going to be doing, like, everything on this page is completely nonsensical to someone that's not had a full semester of Calc 3. And now that you have had that full semester, like, you know how to do all of this. And it could scare a mere mortal away from math forever, I think, if you showed them that at the wrong time. So I don't know. I just think it's kind of like nice to look at this problem, reflect on the semester, and kind of, feel a little bit of pride for all the work that you've done, and the fact that you now can understand some of what's going on here. A problem like this, I mean, just look at this. Look at all that's going on here. It's way too complicated to ask this on an exam. I mean, even as a homework problem, I bet this probably takes you like an hour and a half. Even if you know what you're doing, like if I were to go through and write this whole thing out, it'd take me at least like 20, 30 minutes. So don't expect a problem this in depth on the exam itself. But yeah, I don't know. Something about looking at this problem, I don't know, fills me with zen. Maybe that sentiment's not shared, but I like it and it's my review, so I threw it in. All right. In particular, we're looking at the flex out of these discs that we're going to end up, or out of this cylinder, which we end up separating into 3 different surfaces: a disc in the back, a disc in the front, going out the side of the cylinder. We have to find normal vectors everywhere. We need to make sure they're pointed outward. So, for the one in the back, we've got to make sure that it points in the negative X direction. The one in the front, or the one on top, needs to be pointed in the positive X direction. So there's all that stuff with orientation going on and making sure that you pick the right normal vectors. You've got to look at the shell that goes along the outside. So its normal vector, you also have to make sure is oriented correctly. Yeah, I mean, just look at all of this. There's so much going on. Arrows are flying everywhere as we try to point back to where all this stuff is supposed to go. Yeah, I don't know. I just think it's neat. But that ought to conclude, man, I need to be done talking, this post-exam 3 review. Again, I cursed myself by trying to say that I could get it done in an hour and a half when we started. It has been at least 2 hours since then. So, well, that's what I get, I suppose. Don't ever try to tell yourself how much time math is going to take. Cool. So I'm going to conclude things here, unless someone asks a question that's here live in just a minute. But since this is likely the end of the video, good luck on the final exam. Don't forget it's open note, and just know that I believe in you. And with that, this has been Steve Dragu signing off.